G'day everyone. Last week I posted my first video on YouTube for Peltier devices and I got my very first comment there, and that comment sent me down a little bit of a rabbit hole. I learned something new and then I came up with a potential idea as to why Peltier devices got this reputation for being inefficient. So I thought I'd make a video about that. But first of all, just to recap what I did last week. If you didn't watch the whole video, don't worry, it was a bit long. Basically, I took a Peltier system like this and I used it to cool a volume of liquid about the same as what you get in a can of beer here in Japan. And I did it for 60 seconds and just compared the temperature at the start of the test to the temperature at the end. A little bit of maths, volume of liquid, heat capacity of water. We could figure out what the average cooling was over that 1 minute period. And then I could compare that to the electrical input to the cell itself. I call these things cells, and calculate the COP, or the coefficient of performance, for this. For that particular experiment, I think we got 3.1, which means there was 3.1 times more cooling here than was put into the system from the electrical power. If you want to express that as a percentage, I know a lot of people don't like that way of doing it, but again, you're simply comparing the cooling power relative to the electrical power. Divide those two, multiply it by 100, and people call that the efficiency. All right, I did do another proper test for this. I have a more refined way of measuring the efficiency of these systems, which is to measure the temperature into the cold side and out of the cold side, and measure the flow rate. And again, together with a little bit of maths and the heat capacity of water, you can figure out how much cooling. Using that test, I got 38 watts with 38 watts of cooling with 11 watts electrical input, so the ratio of those 3.45 as a coefficient of performance. Now you might wonder, how can I do those kind of measurements? They're very, very fine temperature measurements. So my business is actually working with medical devices. I've been working in test labs for more than 35 years, and I'm actually selling test equipment for medical devices, and this kind of ratio that gets set up. So you've got medical devices have to be accurate. The equipment that I sell needs to be at least 5 times more accurate than the medical devices. And then the reference equipment that I have here in the laboratory or my office has to be around 5 times more accurate again. So the result is that I've got a whole bunch of very accurate equipment floating around here, which is more than what you would normally have in your own home. Okay, I did want to point out that the COP that you get here, first of all, is well in line with what you would expect from the datasheets for this device. I'm not inventing anything crazy here. And the COP itself is very much tied to that conditions of the test. So it was 3 amps and very little temperature difference, like 1 degree from the hot side to the cold side. In real world applications, you're not going to get that COP. You might get 1, 2, 3, or 4. It very much depends on the conditions of use. Now, I could have run this system here at 0.5 amps, and I could have measured 20 as the coefficient of performance. That's 2000% if you want to use that other way of expressing it. Most people wouldn't believe that you can get a coefficient of performance of 20 out of these, but you definitely can. The thing is, it's not very useful because there's not much temperature difference involved at those kind of levels. But anyway, it is possible. And the other thing is, I don't want to say that these guys are more efficient than, say, an air conditioner. These guys are definitely 2, 3, maybe even 4 times more efficient than these guys. So I'm not trying to say that. It's just that they can stand on their own, and they're definitely a lot more efficient than the advertised 3 to 10%. Okay, so let's get on to the key point of this video, which is, why are Peltier devices got this reputation for not being efficient? I think there's 2 basic reasons. One is that actual implementation for Peltier devices often have a lot of restriction in the thermal circuit outside of the Peltier, and that kind of kills the performance of the system. So it needs to be designed very well. The second one is just this definition of efficiency. We've got people that will complain that you can't get more than 100% efficient. There's thermodynamic efficiency. There's a whole bunch of stuff coming in there which is just muddying all the waters. So I'm going to just go back to that first point, which is the efficiency of the actual setup itself, or actual implementation. So most people would use a heatsink, something like this. I've actually pulled this out of a Peltier fridge, and it's a pretty decent heatsink. It's fairly heavy. And for normal electronics, this would be fantastic. I could use a MOSFET that's running at 100 watts. I've measured this heatsink as 0.5 Kelvin per watt. So you multiply that number by the amount of power that you want to put through here. So let's say I want to run the MOSFET at 100 watts. Go through here, I'm going to get 50 degrees difference between the hot side and the cold side, so the ambient. So let's say the ambient is 25 plus 50, so the hot side of here is going to be 75 degrees, which is fine for a MOSFET. They're normally rated for 150. It's kind of overkill for that kind of thing. But if you're going to put this in a heat pump, any kind of heat pump, not just Peltiers, compressor systems or whatever, it's going to kill the heat pump. And the reason is, let's say this system here, I'm going to run it really hard at 6 amps. I can easily get 100 watts of heat, more than 100 watts of heat that's coming out on the hot side of here. So if I try to pump that 100 watts through here, I'm going to get that same 50 degree temperature difference between the ambient and the hot side of this. That means that for this system, it's only got around 60 degrees for pumping action, as in 60 degrees from the hot side to the cold side of the Peltier system. And if you're going to waste 50 degrees of that with your heatsink, you're not going to get very much pumping action going at all. It should be pretty obvious. And I kind of think of these guys as like driving a car around with the handbrake on. You can still drive the car, but it's not going to be very pretty. It's not just the heatsink, it's also things like using thermal paste, which can be a bit hit and miss. And especially if you are running it hard and this side here is getting very hot, and that thermal paste tend to evaporate and go brittle and stuff. It's not very good. Plus you've got the design on the cold side of the circuit, and insulation and all this sort of stuff. So there's a lot of things that can go wrong with a Peltier system if it's not assembled right. But it's nothing to do with the Peltier itself. It would happen the same if you try to do this with any kind of heat pump. So that's reason number one why we've got this reputation for Peltiers being not particularly efficient. The second one is this definition of efficiency itself, and some confusion around that. I'm going to do a bit of an example here that's might be a little bit into the weeds, but just bear with me. It's a bit of a punchline at the end. Hopefully it will make sense then. So if I took a block like this, a bit of metal here, and I use my arm to raise that up, I'm giving this some potential energy here, and I could calculate the chemical energy that I put into this system and take the ratio of that. I could express it as an efficiency with 100% and so on, probably get something like 25%. But the key point is, for a system like that, I can never get more than 100% efficiency. The amount of potential energy always has to be less than the chemical energy that I'm creating here in my arm. But I can use a bit of ingenuity, a bit of smarts to figure out a better system for lifting that weight. So I've got a counterbalance here, same weight on both sides, pivot point in the middle. With this system, I can use a very small amount of force here to raise the weight on that side here. Now, of course, I'm not doing anything magical here. All I'm doing is kind of stealing the potential energy from this side and putting it onto this side, and a little bit of wasted energy here in the pivot point. If I wanted to define the efficiency of this system, and again, I know people don't like this definition, but I could divide the increase in the potential energy here divided by the energy that I use with my finger here to push this, and I can easily get ratios of more than 1, or with that if percentage way of saying it, more than 100%. So okay, so that's probably nothing special there so far. Heat pumps, of course, do a similar kind of thing. You're using some kind of energy to set up a temperature differential. Once that difference is there, you can get more heat flow going from the hot side to the cold side than you use to set up the temperature differential. You're not creating or destroying any energy, of course, you're just moving the heat around. And if you want to divide the amount of heat that you got to move around by the energy that you put into the system, you can get ratios of more than 1 or efficiencies of over 100%. All right. Until now, maybe everything makes sense. It's run of the mill. Here's the key point. If I wanted to improve the design of this, so basically I have to try and get rid of the friction in the pivot point here. I could keep improving that. I can get more and more efficiency out of this system. More than 100,000, 10,000, even 1,000,000%. It's theoretically possible. Of course, we don't go down to quantum level kind of stuff. For heat pumps, that's not true. There is a theoretical limit for the maximum coefficient of performance that you can get out of a heat pump. And the reason for that is because of the fundamental nature of temperature. Yeah. So with this glass of water here, we tend to think of this as being all the same temperature, as long as it's mixed up a little bit. But the thing is, the individual molecules inside there are doing all sorts of weird and wonderful things. Lots of different speeds and directions and so on. So what we measure when we measure temperature is the average kinetic energy of the energy that's in here, not the energy of the individual molecules. And because of all that randomness that's going on in there, it turns out that that puts a theoretical limit on the maximum coefficient of performance that we can get out of a heat pump. So what does that mean for our Peltiers? Well, the thing is, let's say we're getting a COP of 3 out of this guy for temperature difference of 10 degrees. The theoretical limit for any kind of heat pump is 30 for, roughly 30 for a temperature difference of 10 degrees. So if we compare that COP of 3 against the theoretical limit of 30, divide those two numbers and then multiply that by 100%, you'll get 10%, which is kind of meaningless because, you know, who has a heat pump that can get a COP of 30? Be great if we could invent one, but they just don't exist. So what we want to know from society's point of view is the amount of cooling I can get from this part of the device relative to the electrical energy that I put in here. That's the most important ratio for this system, and for that we can definitely get numbers of more than 1 for a Peltier device. Okay, so hopefully that might explain where this internet wisdom of Peltiers being only 3 to 5 or 3 to 10% efficient. I think it comes from that Carnot cycle, that theoretical maximum limit for heat pumps in general. All right, that's basically what I wanted to cover in this video. There's just those two reasons why we don't get that kind of efficiency that we might expect is from the data sheets. It's because of these kind of terrible heat sinks that get used with Peltiers, and of course the different definitions of efficiency that are kind of muddying the water there. Hopefully you could follow that and found it interesting, and I'm going to be back with more videos on Peltiers in the future, so until then.